This video will cover reaction mechanism. Please read the OER textbook chapter section 12.6 for more detail. When we talk about the reaction mechanism, right, we're looking at how many steps that involve that require the reaction to collide with one another, right, to undergo the productive pathway, right, to become the product. So before we get into more details, I want to use this example of the reaction for the two pollutants to help us understand this whole scenario better. Okay, so in this case, the experimental rate law for this reaction come out to be the second order with respect to the nitrogen dioxide and the zero order with respect to carbon monoxide. Okay, so this is the differential rate law for this reaction. So again, because it's zero order with respect to carbon monoxide, so you can also omit that carbon monoxide. Okay, so you might ask, how can we determine the experimental rate law, right? So this one we already learned this in chapter 12.4. If you don't remember, go watch chapter 12.4. Okay, so again, in order to find out the experimental differential rate law, you will need to use experimental data to help you find out the order of reaction. So now my question is that, well, according to collision theory that we learned in chapter 12.3, right, we learned that for a reaction to occur, it needs to collide with one another, and it needs to collide with proper orientation and with sufficient energy. So how come that if these two need to collide with each other, how come that the rate, right, doesn't depend on carbon monoxide, it only depend on concentration of NO2, right? So you might have that question in mind. Okay, so the next question is that what are the details of the step that involved with this reaction, right? So what exactly happen when these two collide, right? Like what are the steps that required for this in order to yield the product, right? So that's what the question we have. In order to address all of these, it's going to fall into reaction mechanism. Okay, so reaction mechanism will tell us exactly why carbon monoxide doesn't affect the rate, right? So why the rate only affect by concentration of nitrogen dioxide. Okay, so we're gonna take a look at how molecules collide. Okay, so those are going to be detailed steps. Okay, so in order to get into reaction mechanism, there are things that you will need to understand first. Okay, so even though the rate doesn't depend on concentration of carbon monoxide, but note that carbon monoxide is necessary for the reaction to occur. Okay, so without carbon monoxide, you are not going to end up producing carbon dioxide. So that means in this case, carbon monoxide concentration is necessary for the reaction, but the rate does not depend on the concentration of carbon monoxide. But before we get into the detail of the mechanism, I want to tell you the important step for the reaction first. The most important step for the reaction is called the rate determining step. Okay, so the rate determining step is going to be the slowest step. The reason why the slowest step is going to determine the overall rate of reaction is because everything else is going to be determined on the slowest step, right? So for example, it doesn't matter how fast all of these steps previously coming, everything else is going to depend on the last step in this case, right? Because the last step is the slowest. Same thing as well if you have like different funnels like this, right? So the first step is slowest, so therefore in this case, it doesn't matter how the second and the third step is fast, right? It's going to be determined by the first step anyways, right? So the first step is the rate determining step. Same thing if you have second scenario, right? If the second step is the slowest, it doesn't matter how fast the first and the last step is, it's going to be determined by the second step in this case. Okay, so same thing with the last scenario, right? So if you have the last funnel, it's slowest, so therefore, in this case, the last step would be the rate determining step. Okay, so that means keep in mind the slowest step is going to determine the overall the rate of the reaction. Okay, the reason for that is because it doesn't matter how fast the previous or the last step are. It's going to depend on the step that is going to be the bottleneck. Okay. All right, so before we get into more of the detail of the mechanism, things that we need to define would be some of the terminology. Okay, so when we're looking at the types of reaction mechanism, we are going to classify by molecularity of the reaction. What is molecularity? Molecularity is the number of the molecules involved when they come together to react in an elementary step. Now, what is an elementary step? Right? So an elementary step is the simplest step that cannot be broken down. You cannot break this any further. The elementary step tell you exactly what need to collide in the reaction. Okay, so it's tell you exactly. So note that elementary step is not equal to the overall step. Okay, overall step mean you combine several steps together and you're going to get the overall step or overall reaction. Okay, so they are not the same. Okay, so elementary step cannot be broken down. Okay, so elementary steps show you exactly what happened. So here, for example, okay, so if you have two molecules, nitrogen monoxide and ozone, when they collide, okay, so these show the collision of the two molecules. This collision is what we refer as elementary step. Okay, so some elementary step lead to an ineffective collision, right? Lead to the product we do not design. Okay, so which is going to be like unproductive collision that we saw earlier, which is part of the collision theory, right? Some collision might lead to the effective collision, right? That is going to lead to the what we call the desired product that we want, right? So in this case, each of these how they collide, right? So each of these are going to be what we refer as elementary step. Okay, so it tells us how they collide. Now, since you know what is the elementary step now, so I'm going to tie this back with the molecularity. Okay, so if you have the elementary step that involved with just one molecule, for example, in this case, one molecule of A. Okay, so the molecularity of this elementary step is going to be called unimolecular. And the differential rate law for this can be written as rate equal to K times A. Okay, so this would be the first order with respect to A. Note that when we are dealing with elementary step, because elementary step cannot be broken down any further, it's a simple step. Therefore, we can determine the rate law by using the number of the molecule of the elementary step. Note that this is only work if you're looking at elementary steps. Okay, so it doesn't work when you're looking at the overall reaction. Okay. Now, if you are looking at elementary step that involve with two molecules, so it can be either two molecule of A or one A and another one is B molecule combined, right, to produce product. This type of elementary step is what we refer as bimolecular reaction. Okay, so the rate law expressed for this is going to be rate equal to K times the number of molecule that involved with the elementary step, right? So in this case, since it involved with two molecule of A, therefore it's going to be A squared. Since this one is involved with A and B, so it's going to be A times B. Okay, so that means these two are going to refer as second order, right? Because involved with two of A and then one of A and one of B for this one, so it's going to be second order. Okay, you probably notice that the elementary step is actually tell you about how many molecules they are going to collide, right? And that's going to how it's going to affect the rate. So now if you look at this, right? So elementary step tell you exactly what happened to the rate, right? So since the collision involved with 2A, so therefore the rate is going to involve with those concentration of 2A. Okay, so and second condition here, right? So since the elementary step involved with both molecule A and B, therefore the rate is also going to involve with the concentration of A and B as well. Okay. Now, if you have three molecules that involve with elementary step, for example, it can either be 2A and 1B or A, B, C, or like 1A and 2B or whatever, right? So all of these are called thermomolecular reaction. Okay, so the rate expression for this is going to involve with all of those molecules in the elementary step. Okay, so this one would be 2 of the A, so that's why we have A squared and then multiply by B. So this one, since involved with each one of these, so you are going to multiply with each one of those. Okay, so all of these are represent third order of reaction. Okay, so 2 plus 1, so that third order, right? So 1 plus 1 plus 1, so that third order. Okay. Again, note that this reaction right here, when you are looking at the rate law, the reason why we are able to looking at the number of molecule is because of these are elementary step. If you have the reaction that are not elementary step, you cannot using this way. You cannot look at the number of molecule and then write the rate law. You need to determine by the experimental data. Okay, so again, for the reaction that is not elementary step, you need to determine by experimental data, which is covered in chapter 12.4. Okay, if you have elementary step, then you can use the number of molecule to write out the rate law, which is covered in 12.6. Okay, so those are the two different things. Now we are going to apply what we just learned right into the reaction mechanism. Okay, so the reaction we are going to take a look at is going to be the reaction that I introduced at the beginning of this lecture. Okay, so we're going to look at the reaction between two pollutants again. Okay, so we see previously, right, the first question is how come that the rate doesn't depend on the concentration of carbon monoxide, right? So, and the second question is, what is the detailed step for this reaction, right? So that means we are going to take a look at the reaction mechanism for this particular reaction here. So let's say that the scientists proposed two mechanisms for this reaction. Okay, so mechanism A is going to involve with molecule of nitrogen dioxide react with carbon monoxide right away, right, to produce the product. And mechanism B, right, involved with the two-step reaction, right? So it's involved with elementary step 1 and elementary step 2. Elementary step 1 involved with the two molecule of nitrogen dioxide react with one another or collide between each other to produce this species right here. And then one of these species right here is going to collide with carbon monoxide, right, to produce eventually product. So since there are two proposed mechanisms, so which one exactly is going to be the valid mechanism then? Okay, so what we are going to take a look at is, let's take a look at A first. Okay, so A, elementary step. Okay, so since we talk about the rate, so that means in this case, when these two collide, it's going to undergo with a certain rate of the reaction. So I'm going to give this forward rate constant equal to K. Okay, so I don't know what it is. I'm just going to use K in this case. Okay, so that means this reaction is going to involve with a certain rate constant. So since this is the elementary step already, okay, so we can say that the rate law for this elementary step is going to equal to the K, right? So this is the K times concentration of NO2 times concentration of carbon monoxide. Okay, so the reason why I'm able to write this is because, as I mentioned earlier, right, when you see the elementary step, the rate law can be determined by the molecule that involved within that elementary step. So that's why I'm able to write the rate law for this one. Now, in order to prove whether this mechanism is valid or invalid, you have to look at two criteria. One is the overall reaction, and the other one is the rate law. Okay, so the overall reaction for the mechanism have to come out equal to the given reaction. Okay, so in this case, since mechanism A involved with just one step, and this one step here is identical to this given overall reaction, so that means the overall reaction for this is going to match, right? So that's correct. Now, the second one is we will need to check the rate law. Okay, so the rate law for mechanism A, okay, if you compare this with the rate law of the experiment, you will see that they both do not match. Okay, so this experimental rate law state that it's going to be second order with respect to concentration of nitrogen dioxide, right? Zero order with respect to concentration of carbon monoxide, but these are not the same. So that means the mechanism A is invalid, right? Because the predicted rate law, which is the rate law from the mechanism A, doesn't match with the experimental rate law. Okay, so that means in this case, we how the reaction occur is not going to be just these two combined. Okay, so now let's take a look at mechanism B. Okay, so mechanism B is going to involve with two steps here. First is two molecules of nitrogen dioxide collide with each other, right, and then produce these two species. And then one of these species is going to react with carbon dioxide, right, and it's going to produce the product, right? So it tells us as well the first step is slow. Okay, so that means first we will need to write out the rate law for step 1 and 2. Okay, so rate law for step 1 is going to be rate equal to K1, right, times NO2 multiplied by another NO2, which is equal to actually K1 times NO2 square, right? Because if you multiply the same thing, it's going to be square, right? And then the second step would be rate equal to K2, right, multiplied by NO3 times CO. Okay, so we have two rate law. Okay, so you can write from the elementary step 1, and you can also write from elementary step 2. Okay, all right. So the overall reaction. Okay, so now the next thing is you need to combine this. Okay, so the overall reaction is when you combine the reactant together, right, and you also combine the product together. Okay, anything or any species that appear on both sides of equation, on both sides of arrows, you cancel those out, right? So if you do that, you are going to get so you can cancel this NO2. Okay, so you can cancel one of these, right, because there are two molecules here, and then you also can cancel NO3, right? So that means the overall reaction come out to be NO2 plus CO going to NO plus CO2. Note that the species that is being produced during the reaction and being consumed is going to be called intermediate. So that means in this case, NO3 is going to be an intermediate for this mechanism. Okay, so which step is the rate determining step? Well, it said the step 1 is the slowest, right? So that means in this case, step 1 would be the rate determining step. So that means because step 1 is the rate determining step. So that means the overall the rate of this reaction is going to be determined by step 1. So that means the predicted rate law is going to come from step 1. Okay, so it's going to be this one right here. Okay, so again, the reason why I'm able to use this because it's come from step 1. Okay, because step 1 is our rate determining step. Now, the next thing is we will need to prove whether this mechanism is valid or invalid, right? So the first one is we need to check the overall reaction. Okay, so the overall reaction that is proposed here come out to be identical to the actual overall reaction of the experiment, right? So those are the same. And the overall predicted rate law that come from mechanism B is also the same as experimental rate law as well. So that means this mechanism B is valid, right? Because the predicted rate law and also the overall reaction, they both match with the experimental data. Okay, so now you might see this. Okay, so this is valid but not proven to be correct. Why do I mention that? Okay, so in order to prove whether mechanism B is correct or incorrect, you will need to do further experiment, like do some further investigation. For example, you might need to try to capture the intermediate, right? So for example, if you are able to capture intermediate and the intermediate come out to be NO3, then that this mechanism probably going to be the correct one, right? Because it's actually go through this step that produce this intermediate. Now let's take a look at the reaction coordinate diagram. Okay, so my expectation is you need to be able to relate the mechanism with the reaction coordinate diagram that we learned previously. So the reaction coordinate diagram is going to be plot between reaction progress or time, right, against the energy. Okay, so in this case, it's giving us 2 steps. So that means you are going to see 2 steps here. So this is slow step, right? So this is, we already see is K1, this is K2, right? So that means in this case, step 1, we are going to start with NO2, react with NO2, which means these 2 molecules, they are going to collide with each other. Okay, so as it collide, right, they need to collide with proper orientation, right? So that means it's going to go to the transition state. Okay. And because it's going to be the slowest step, so that means it's indicate that the activation energy of this step would be very high, right? So it's going to achieve this transition state. So I'm going to call transition state 1. Okay, so because again, this is a very slow step, so that means it's indicate that the activation energy of this step right here, the forward direction, is going to be a huge value. And then this transition state is going to become intermediate, right? So we have intermediate there. Note that this one, NO, is actually part of the product. So I'm going to write that later. So I'm going to actually write out the intermediate first, NO3. You might ask me, hey, can I draw NO3 down here or NO3 up here? The answer is yes, we can do any of those. Okay, so the reason for that is because the problem doesn't give us any other information. Now, if you're looking at the second step, right? So the second step involved with the collision between NO3 and carbon monoxide. So I'm going to add carbon monoxide here. Okay, so remember this step is fast. So therefore the activation barrier of this is going to be a lot less than the first step. Okay, so the EA of this is going to have to be smaller than the first step. So this is step 2, this is step 1. Okay, so it's going to go to transition state 2, right? So transition state 2 is involved with the collision between NO3 and CO. And then after this would be the product, right? So note that the reaction coordinate diagram that we need to draw is going to be of the endothermic process. So therefore, in this case, because of endothermic process, so your final answer, which is the product of NO plus CO2, right? So that's the product, would need to be higher than the reactant, right? So the energy here have to be higher, right? Because this is going to tell you about the enthalpy change that is positive, that indicate is endothermic. Okay, so that means this one involved with 2 steps. So therefore, you are going to get 2 activation barriers. You're going to get 2 transition state, and you are going to see the intermediate. Okay, so on the exam, you can write this as reactant, right? TS1, EA1, and this is going to be intermediate, right? And then TS2, EA2, and then this one would be product. You can write me that as well. Okay. If the problem gives you the exothermic instead, then the level of this energy for the product have to be lower than the reactant. Okay. All right, so let's take a look at example 1. Okay, so in this case, I want you to do the same thing as I mentioned earlier. Okay, so try to do your best to fill this blank. And when you finish, resume the video again to check your answer with me. All right, let's check your work together with me. Okay, so this one, we are given the reaction between 2A plus E. It becomes 3D, right? So this reaction is exothermic. Okay, so this is the experimental rate law. Okay, so again, the experimental rate law is going to be determined from the experimental data, similar to the one that we did in chapter 12.4. Now below here is the proposed mechanism of the above reaction. Okay, so we have 3 elementary steps. Okay, so we have these 3 elementary steps for this proposed mechanism. Okay, so each of these, because these are elementary steps already, so that means we should be able to find out the differential rate law for each of these elementary steps right away. Okay, so elementary step 1, the rate law would be rate equal to K1, okay, multiplied by concentration of A and B. Okay, step 2 would be rate equal to K2 multiplied by concentration of C and E. Okay, step 3 is going to be concentration of F multiplied by A. Okay, so the next thing is we are going to take a look at the overall reaction. Okay, so in this case, for the overall reaction, you will need to combine reactants together, right? Product together, and whatever species that appear on both sides of the equation, you can cancel those out, right? Whatever that left over would be what left in the overall reaction. So in this case, we can cancel C, right? We also can cancel F as well. And we also can cancel B. Okay, so that means the overall reaction come out to be 2A, right? Because we combine this 2A plus E is going to give us 3D. Okay. All right, so is there any intermediate? Yes. Okay, so the definition of intermediate is it's going to be produced during the reaction, and it's also going to be consumed or being used up during the reaction as well. Okay, so C is produced and is also being used up. F is also being produced and also is going to be used up. Okay, what is the catalyst then? Okay, catalyst is something that you add to the reaction and then it's going to not being consumed. Whatever you add at the end is going to give you that catalyst back. Okay, so catalyst will not be used. Okay, so if you input the catalyst, right, at the beginning of reaction, at the end, you are going to obtain the catalyst back. The example of that is going to be B. Okay, so for example, you input B, right, at the end it's come out, right? So that means in this case, B is not used up. So B is going to be the catalyst. Okay, so note that catalyst is not going to be generated. You actually add it first, right? Whereas if you're looking at intermediate have to be produced first before it's used up. Okay, so those are different definitions. Okay, so now which step is the rate determining step? Okay, so it's going to be the slowest step, right? So it's going to be step 1. And because step 1 is the slowest step, so step 1 is going to determine the rate law. So that means the rate law for the predicted rate law or the rate law for this mechanism is going to come from step 1. Okay, so it's going to come from this step right here. Okay. All right, so is this proposed mechanism valid or invalid? Okay, so now let's check this. Okay, so if you're looking at this mechanism, the overall reaction, okay, is matching with the experimental data. Okay, and the predicted rate law also the same as experimental rate law as well. So that means in this case, this proposed mechanism is valid. Okay, but again, it's not proven to be correct. If you want to know whether it's correct or not, you need to conduct more experiment. Now let's take a look at the reaction current diagram. Okay, so you are going to plot between energy and reaction progress. Okay, so step 1 is the slowest step. So that means the activation barrier have to be the highest. Okay, so I'm going to start with reactant. Okay, so go to TS1. Okay, so the EA1 will have to be the biggest value. Now it's going to produce the intermediate, right? So intermediate 1. Now intermediate 1 is going to go through second step, right? So second step is faster. So that means it's going to be a relative high EA as well, but it's going to be smaller than the first EA. Okay, so this would be involved with transition state 2. And this transition state 2 is going to yield the second intermediate. Okay. And it said that the third step is the fastest. Therefore, the amount of EA for the last step would be the smallest. Okay. And this reaction is giving us exothermic. So therefore, in this case, the product that is being produced have to be in lower energy than the reactant, right? So in this case, this one right here have to be lower to give us delta H to be a negative value. Okay, so this would represent the reaction coordinate diagram for this proposed mechanism. I want you to actually read this case study. It's going to be on the OER textbook, page 297 to 299. Okay, so in this case, you are going to be able to see what you learn in class. Okay, so and you are going to apply that in real life case study. Okay, so you are going to see this and it's very fascinating. So I want you to actually read through it. It's only like a couple pages. Okay, so please just take time to just read through. Okay. All right, so for this lecture video, we're looking at reaction mechanism, right? We're looking at several terminology, right? Elementary step, molecularity, and things like that, right? We determine which one is the rate determining step, right? We're looking at which mechanism is valid or invalid. We're looking at what would be intermediates and what is the catalyst. Okay, so after this lecture video, you should be able to start working on homework 12.6.